Hey guys, welcome back to another video. In this video, we'll be learning about optimization problems, also known as applied minimum and maximum problems. So, these problems can be broken down into 5 primary steps. The first step being write all given quantities and quantities to be determined. The second step being write a primary equation for the quantity to be minimized or maximized. The third being rewrite the primary equation to be an equation with one variable. The fourth being determine the feasible domain. And the fifth being determine the minimum or maximum value of this equation. So take a moment or two to copy this down in your notes because these are important steps. And we'll get right on to our first example problem. So I'm assuming that you copied this down in your notes, but let's move on to our first example problem. So our first example problem asks us to find two positive numbers that have a product of 147 and the sum of the first number plus 3 times the second number is a minimum. So what we know that there is two positive numbers and that the product of them is 147 and the sum of the first plus 3 times the second is a minima. And what we don't know is what these two positive numbers are. So I don't know if this seems obvious or not, but this is just writing a unifying equation. It's very similar to what you would do in a rates of change problem. So two positive numbers multiplied by each other is equal to 147. Let's call these positive numbers x and y. So x times y is equal to 147. The sum of the first, so we'll call x the first number, plus 3 times the second number is a minimum. So x plus 3y is equal to, and then we'll say s for sum. So x plus 3y is equal to a sum. And we know that this sum has to be a minimum, like so. And now what we do is we have to rewrite the equation with one variable. And in order to do that, we have to first get everything into one variable. So what we can do here is substitute. So we learned that x is equal to 147 divided by y. So that would just be x divide y by both sides. And knowing that, we can use this equation right here and substitute x in. So 147 over y plus 3y is equal to s, like that. Now, what we need to do is determine the feasible domain. So these are two positive numbers and their product is 147. So we know automatically that they must be greater than 0, but they can't be 0 because if they were 0, then the product would be 0. Now, our next step here is to find the derivative. So if we were finding the derivative of this, then this would be equal to, at first, let's actually rewrite this to make it easier on us. This would be 147 times negative y plus 3y is equal to s. Now we'll take the derivative with respect to y, since y is the common term. Y is the common variable here. So if we take the derivative, this would be equal to negative 147 over y squared plus 3 is equal to ds over dy. And if we had to find the relative minimum or maximum, we'd have to find our critical numbers first, which if you don't know how to do, I suggest you check out the calculus playlist that I will have linked in the description. It has a lot of calculus videos in it that will help you pass your class, hopefully. So, but what you need to do is set ds dy equal to 0. So let's do that. And if we do this, we see that we can simplify this to be negative 147 y squared is equal to negative 3. Let's multiply both sides by negative 3y squared, and we'll do it up here. So if we multiply both sides by negative 3y squared, we get this is equal to like so. Now we can divide 147 by 3. We get 49. 49 is equal to y squared, and we get that y is equal to 7. Now let's circle that, or let's box it up in orange. Now, what about our x value? Well, we know from earlier that x is equal to 147 over y. So we can write in from here that x is equal to 147 over y, which is equal to 147. And we now know that y is 7 over 7. And this is equal to 21. So we know that for a minimum sum, while the product is still 147, one number must be 7 and the other number must be 21. So take a moment or two to comprehend this in your notes, copy it down, remember how to do it, and we'll move on to our next example problem. So for our next example problem, we're asked to find the length and width of a rectangle that has a perimeter of 100 meters and a maximum area. So we know that it's a rectangle, it has a perimeter of 100 meters, and we know that we need to find the maximum area. What we don't know is the length and width. So the first thing that we can obviously do is write the unifying equation. So if the rectangle looks something like this, then we know that the perimeter is equal to 100 meters. So we can write 2x plus 2y is equal to 100. And for the area, we can write x times y is equal to area. And we know that it must be a maximum. So we'll write maximum like so. Now, what we need to do is find a variable to substitute in, and we can take that from up here. So if we say take x for example, 2x is equal to 100 minus 2y. X is equal to 50 minus y, like that. Now, using this information, we can take this and plug it in so that we get that 50 minus y times y is equal to area, which in turn is equal to 50y minus y squared is equal to area. Now we have to find the derivative of this, and derivative of this would be equal to 50 minus 2y is equal to dA dy. So now that we have that, we can find the relative minimum or maximum by setting dA dy equal to 0. And we can do negative 2y is equal to negative 50. Y is equal to 25, like that. Now, what about x? And actually this would be 25 meters. Now, what about x? Well, we know from earlier that x is 50 minus y. So x is equal to 50 minus y. X is equal to 50 minus 25 is equal to 25 meters, like so. So take a moment or two to copy this down in your notes, and when you're done, come back to the video, please. Now, for our final example problem here, this one is a little harder than the rest. We have a rectangle is bounded by the x-axis and the y-axis and the graph of y is equal to -1/2 x plus 3. What length and width should the rectangle have so that the area is a maximum? So, we know that there's a rectangle. It is bounded by the x-axis, y-axis, and this graph right here. And actually, I'm just gonna do an arrow to it like that. And now we need to know what the length and width is. So if we can find it real quick, we need to know what the length and width is so that the rectangle has a maximum area, like so. Now, this upper part right here is a bit hard to understand, but it essentially means that here's the x-axis, here's the y-axis, and here's your graph. And it essentially is asking if we have a rectangle that stays within this graph and this y-axis, or this and this graph, then what can be the maximum area? Well, we could draw a rectangle like this. We could draw it like this. We could draw it like this. We could draw it many ways, but it's always asking when will the area be the maximum, and if so, what is the length and the width? So we have to write a unifying equation for this, and we're asked for area, so we'll write x, y is equal to area, with x meaning the width and y meaning the length. And this isn't actually how it's supposed to look, but this will be the example we'll use. Now we need to find something to replace with, and we can use y right here from the y equals -1/2 x plus 3. So we do x -1/2 x plus 3 is equal to area, and this would be equal to -1/2 x squared plus 3x is equal to area. Now we have to take our derivative of this, which would give us -x plus 3 is equal to the derivative of area over dx. And if we want to find our relative minimum or maximum, we set this equal to 0, like so. And we get that x is equal to 3. And then for y, we know from here that y is equal to -1/2 x plus 3. So we'll write that in like that. And we know that x is equal to 3. So we get that y is equal to 3/2. Like this, like this. So if you found this video helpful, please consider subscribing to the channel. It would mean a lot. And if you're having trouble with math, check out the Calculus and Algebra 2 playlist that we have linked in the description. So, as always, have a nice day, and I'll see you guys next time.